Okay, we are now ready to begin our review lesson. This is our second to last review lesson. Today's lesson is going to be graphing calculator skills. And the first handout that I attached to the assignment in Google Classroom is a whole bunch of information about how to find some important things in the calculator. So finding points on a graph, finding y-intercepts, finding x-intercepts. These are all skills that I know that you already have, but I thought you might like to have this handout. Here's some troubleshooting things that can go wrong. Changing the viewing window, finding maxes and mins, how to graph absolute value, and some other tips and tricks for a calculator. All right, so that's a very good handout to print or to save for future reference. And let's go ahead and do some problems. For today's problems, we're going to do the practice right in here. There's going to be no additional practice set. So we're going to review graphing on a calculator, and I did sneak in a little extra review and 2 little previews from calc because it was a good time to do that. So first, let's practice finding x-intercepts and the maximum of that trig function. Make sure you grab your calculator and do this practice with me. Okay, so when you go to graph this, please notice in my calculator, I'm actually all set up for all the problems already. I don't expect you to do that, but you see how I have all these equations in here already? And it's okay to have those because if the equal sign is not highlighted, it's not going to graph it. So this one down here, that's what we're going to do for number 2. If the equal sign were on, it would graph it. If I deselect that by going over the equal sign and hitting enter, I can turn that graph on or off. So that's a nice way to store your equations without actually having to graph them. So I want to graph 3.2 sine 2x minus 3 minus 1. Watch the parentheses. Make sure your mode is radians whenever you're graphing in trig. And you can do zoom standard or zoom trig. I guess I'll go zoom trig. If you have the slightly newer graphing calculator, your window is going to be a little longer than ours, but it's not a big deal because we're about to change the window anyway. Because we're told to do this on the interval from 2 pi to 3 pi. So if you look on the handouts, the handout that I just showed before, changing your viewing window is something you need to be able to do. So we want to go from 2 pi to 3 pi. That's our x min and our x max. And notice when I type 2 pi, the calculator converts it to a decimal. That's okay. And when I type 3 pi, the calculator converts it to a decimal. If you stayed in zoom standard, your x scale will be 1. That means your tick marks will be going 1, 2, 3, 4. If you change to zoom trig like I did, your tick marks will go by 1.57 or pi over 2. So pi over 2, pi, 3 pi over 2, and so on. Either way is fine. It doesn't matter. Okay, so let's take a look at this part of the graph. Here's an x-intercept, a max, and an x-intercept. That's what we want to find. We weren't asked for the minimum in this particular problem. So to find an x-intercept, it's second trace 0. Second trace 0. Full instructions are on the handout, but just to remind you, we go to the left of the x-intercept and hit enter. We go to the right of the x-intercept and hit enter. We go as close as we can and take our guess. And you might not pick the exact same left bound, right bound guess that I do. So I picked here for my left bound. You might have picked here or here or here, and that's okay. We don't have to have the same exact left bound, right bound guess. Okay, so that's where my guess is going to be. When I hit enter, the calculator is going to run a program and give me a very nice decimal approximation for that x-intercept. So let's go ahead and round to 4 decimal places. I forgot to put in the directions what to round to. 7.9421. And I do want the coordinates, so if it says coordinates, you need to give that as an x and y. Almost all the time this year I ask for coordinates. In AP Calc next year, it's going to be sometimes coordinates, sometimes just the x values. So we'll learn to distinguish based on the instructions which one we want. For the other x-intercepts, it's second trace 0 again, and you have to repeat that process over here. Left bound, right bound, and your guess. So this one's 9.19510 for that x-intercept. In class, I always required that you make a sketch of the graph. So if you want to sketch it, you can. Calc next year, sometimes required, sometimes not. Since I changed the window, I'm going to go ahead and note that it went from 2 pi to 3 pi. And then we want to find the coordinates of that maximum. So for a maximum, it's second trace maximum. And by the way, when you go to select second trace maximum, just to remind you, you don't have to scroll down to 4. You can, it's not a big deal. But when you hit second trace, if you want to find the maximum and use that operation, you can just hit the number 4. It's a few fewer keystrokes, so it's kind of good to be aware of. And again, this is the left bound, right bound, and the guess. So go to the maximum, go to the left. I'm going to go here. You might go here. You might go here. You might go here. Anywhere, just a little bit to the left. Don't go too far. Don't go all the way down here, but just make sure you're to the left of the maximum. Make sure you're to the right of the maximum. The calculator is going to put these little markers here to just acknowledge that we told the calculator our max is between those. When we go and take our guess, we end up with this as our maximum. So that's 8.5689, and that's our max. And I want to take you back for a second because I forgot to mention something before. When you go to find these x-intercepts, I just want to show you, I don't think it happened when I did it before, but depending on the left bound, the right bound, and the guess that you pick, sometimes you'll get something funny like this for the y. So I want to remind you what that is. So this is the x-intercept here, which is the 9.1591, 9.1951. Okay, so this right here says 2.69 e negative 12. Negative 2.69 e negative 12. So sometimes when you're finding an x-intercept, you'll get a number like this where it has an uppercase E and then a negative number after that. That represents scientific notation. So what this represents is times 10 to the negative 12. And when you have times 10 to a negative power, what that tells you to do is move that decimal point 12 places to the left. So you would take that decimal point and go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. That's a lot of zeros that you're going to have to fill in. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. There's 11 zeros before you get 269. So no matter what you're rounding to, 4 places, 5 places, even 8 places, that's going to be 0. And you may not have negative 2.69. So when you did this, you might get 3.5 e negative 14. So you could even get a positive out front. But it's this part that's really critical here because that stands for times 10 to the negative 14. So what that represents is moving the decimal point 14 places to the left. So it's going to be a whole bunch of zeros. That's not even enough of them. There should be 13 zeros before you get to 3.5. That's as good as 0. Okay. Some other things we could now figure out if we wanted to that we might want to figure out in calculus class, aside from x-intercepts and maximums, minimums, sometimes we'll find those. But I feel like if we practice max, you could do a min. Sometimes we'll be interested in when we're above or below the x-axis. I have one of those coming up. And sometimes we even will put in a second graph or a horizontal line and find points of intersection. So if I had y equals 1.5 going through that graph, you could find the points of intersection by doing second trace intersect. So second trace intersects, and you just go as close as you can and basically hit enter, 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 and you'll get the point of intersection. You'll know you're finished when it says intersection. And just to show you that over here, if you wanted to find this point of intersection, see how right now I'm on y1? I'm on the sine curve as I get over there. So I'm on the first curve, the sine curve. I hit enter. That puts me on 1.5. If you're doing this, this might be y2 for you instead of y5. And I hit enter, and then I take my guess. I can just stay where I am. The calculator runs a program and tells you the point of intersection. So lots of things we can do with the calculator, but for this particular example, it was just those x-intercepts and the maximum. Okay, for the next example, we're going to find a maximum as well. So let me go in here. I'm going to clear out that previous graph and that horizontal line that I used. I'm going to select this function right here. If you have a slightly older graphing calculator like the one I'm using, when you go to abs, that's math, you arrow over to num, and you select abs. Okay, so if you go to select abs on an older graphing calculator, actually put ABS, and then you need to put all that in parentheses. If you are using a slightly newer graphing calculator, when you hit math and arrow over to num and select abs, it's actually going to show you those absolute value bars. So then you can put x minus 3 squared minus 5 in there and get your graph. Okay, so I'm going to go back to Zoom Standard. That's Zoom 6. Again, you don't have to scroll down to 6 to hit enter. You can just hit the number 6. It'll take you to Zoom Standard. And that's what your graph looks like. And what we're interested in here is the maximum. So for this graph, we want to know what the maximum is. And again, I could ask you all different things. I could ask you where your graph changes from increasing to decreasing. That would also be asking for a maximum. I could ask you where the x-intercepts are. I could ask you for the y-intercept. Lots of things we might want to know about this graph. But right now, it's the maximum that I'm interested in. So I'm going to go over toward that max, do a left bound, a right bound, and a guess. And if I'm rounding to 4 places, I get 3.5 as my value for that maximum. One thing that's kind of neat on this problem is if you go to find the minimums, the minimums are also x-intercepts because they're touching the x-axis there. So if you go to find a minimum, if you do your left bound, your right bound, and your guess, you'll get this right here. And remember, this is pretty much 0 because this you would move your decimal point 6 places to the left. So we're rounding to 4 places. That's 0. Okay. So this is the location of your minimum, 0.76, around 0.76. And if we were to do an x-intercept instead, because these minimum values are also x-intercepts, we're going to get the same answer. And that doesn't happen too often. That only happens if your max or min is actually on the x-axis. So kind of neat, just wanted to point it out. Something else I want to point out about this is a little preview for calculus, because I'm sure you notice the absolute value here. Do you notice the inside function is just a basic quadratic? So let me take you over to Desmos real quick. Okay, on Desmos, here's the absolute value graph that we're looking at. What absolute value does when you put it around an entire function is it takes anything that's below the x-axis and flips it up above the x-axis. So if we look at the parabola itself, moved right 3, down 5, as shown, what you want to do is picture this part. When we put absolute value around the entire equation, that part is just going to flip up, and that's how you get the green graph. So that's kind of neat in my opinion. Sometimes it's easier to see on paper. So I just wanted to take you over here and show that to you now. So if we were to graph the parabola itself without the absolute value, it would look kind of like that. When you put absolute value around any function, not just parabolas, what happens is the part that's above the x-axis will stay there, or on, above or on stays where it is. And then the part that's below flips up and gives you a mirror image. So that's what happens when you take the absolute value of an entire function. And those of you who've taken physics might recognize that from comparing velocity and speed graphs. And let me take you back over to Desmos real quick just to show you that really works with any function. So if you think back to the sine graph that we did in the first one, and if you take a look at that sine graph, if you put absolute value around that entire equation like shown here, anything that's below the x-axis is going to flip up. So this part will stay where it is, but this part is going to flip up. This part will stay where it is, but this valley down here is going to flip up and be a taller hill. So that's the impact of putting absolute value around an entire function. So that's a little calc preview. It's not something you need to know over the summer. It's not something you need to know when you walk into calc next year. But these, I did that in class too. When you get a little preview, sometimes it sticks and it just makes next year easier for you. Okay. Up next, for what values is this function above the x-axis? So let's go ahead and use our calculator for that. So you can type x squared minus 10x in there. And I'm going to go back to Zoom Standard. I think I was there already. And we want to know where above the x-axis. This is just a parabola, so I can't really see it too well right now, so let's practice changing our window. I want to see further to the right. I don't technically have to, but I want to because I want to see this parabola. So I'm going to go, I changed my x max to 15. You might change it to 12. You might change it to 20. And I want to see down further. So I'm going to go to my window and I'm going to change my y min. You might try negative 20 first. You might try negative 50 first. If it's not far enough down, just decrease it. And if it's too far, just go back in and change it again. There's no set formula for how to get a great viewing window. It just depends on the problem at hand. So I'd actually like to go a little further. And again, to actually answer this problem, I don't have to change the window. I just wanted to seize the opportunity to review changing the window with you. So this is the window that I currently have, and I think that looks pretty good. So I want to know where this graph is above the x-axis. Well, the part that's above the x-axis is this part and this part. So to find out where we're above the x-axis, we need to know what those x-intercepts are. So I can go second trace 0, left bound, right bound, and guess. And that is 0, 0. And second trace 0 over here for the other x-intercept. And that is 10, 0. So to answer the question, we don't want to give those actual x-intercepts. We want to give a set of numbers, a solution set. So where we're above the x-axis is to the left of 0, not including 0 because it says above. If it said or equal to, we'd put a bracket on there, and anything to the right of 10. That's interval notation. If you would prefer to say x less than 0, x greater than 10, you can. Next year in calculus, we go back and forth between interval notation and inequalities. So a lot of times you have your choice, but you just have to be familiar with both. And when you look at this problem, at some point did you say, you don't need a calculator for this, Miss P, what are you doing? So let's take a moment to review something from the past to show how we could have done this without a calculator. For this particular function, with a more complicated function, we might need a calculator. So let's take a look. I have x squared minus 10x. Above the x-axis is the same thing as saying that that function is greater than 0. This is a quadratic inequality. We solved these in chapter 1 when we were doing some slightly different domains. So within our work for finding domains, we sometimes solved a quadratic inequality. So to solve a quadratic inequality, we look to factor, or sometimes we take square roots, but you can't set each factor equal to 0 now because there's an inequality. And when we had square roots, remember we couldn't take the square root of both sides because it's an inequality. So we had to play a different game to figure this out. So what we did back in chapter 1 is we made a number line. And on that number line, we selected 2 important points. For this one, it's 2 points. It's where the function is going to be 0. So this will be 0 when x is 0, and this will be 0 when x is 10. And for this particular example, it splits our number line into 3 intervals. And then what we did is we tested x values. So we picked an x to the right of 10, like 11, 15, 20, whatever you want over there. And we didn't actually do all the work to plug in. We just wanted to find out if it would be positive or negative. So if I plug in 11, that's positive. And if I plug in 11, 11 minus 10 will be positive, and a positive times a positive is positive. Hopefully this looks familiar. And then in between here, in between 0 and 10, we want to test something between 0 and 10. You can test 1, you can test 5, you can test 8. I'm going to test 5. I'm going to go right in the middle. And again, I don't actually need the numerical value. I just need to know whether it's positive or negative. So if I plug in 5 to this right here, that's positive. If I plug in 5 here, that comes out negative, and a positive times a negative is a negative. So by testing 5, that represents all the x's in this entire region. And it says that here, in between 0 and 10, no matter what I plug in, I'm going to get out a negative number. And then I want to test something to the left of 0, like -1 or -5, whatever we want. When I plug in -1, this is negative. When I plug in -1, this is negative, and a negative times a negative is a positive. And what that number line represents is where the graph is above and below the x-axis. So if we think about the graph we just made, it's above the x-axis to the right of 10. That's what that plus represents on the number line. And it's above the x-axis to the left of 0. And it's below the x-axis, or negative, in between 0 and 10. So I wanted to take you back to this review topic from chapter 1. We haven't done that in a long time, but it's going to show up again next year. So again, this is a skill that we don't expect you to walk into AP Calc with that skill next year. But when it comes up, we expect it to come back to you pretty quickly. So I thought it would be good to throw it in a little bit today. Another way to solve this, by the way, is you could just graph this by hand. This is just a parabola with x-intercepts at 0 and 10. So your knowledge of quadratic functions might allow you just to graph that. You know it opens up because the leading coefficient is 1, and the end behavior rises left, rises right. So by having all of these tools, because you've learned so much, you have multiple ways to solve this problem. You know how to use a calculator, you know how to represent your answer in interval notation or inequalities, you know how to graph this without a calculator, and you can even solve that algebraically without ever looking at the graph. All right, last problem for today. You still have one more lesson. Graph to determine the solution set to this right here. So let's go ahead and graph that. And so I threw in an e to the x. I'm not in Zoom Standard. I'm going to go back to Zoom Standard. So I threw in an e to the x here. E, remember, is that special number called the natural base. And this is what my graph looks like. And when you take a look at it, you can see here we're below the x-axis. Here we're above. I'm not quite sure what's going on over there. So if we hit trace, we can kind of look. See, my y value is positive. As I keep going to the left, it actually crosses over and becomes negative. So I'm below the x-axis now. And then if we look, the x value continues to be negative. And it's getting closer and closer to 0, but it's actually going to stay below the x-axis forever. That's because of that e to the x being involved. There's actually an asymptote in there. So let me go back to Zoom Standard. And we want to, oh, that's interesting. We want to determine the solution set to this. So it didn't actually say, it didn't actually tell us graph y equals this function, but since it said graph, I went ahead and graphed this expression right here. And if we wanted to determine where this is greater than or equal to 0, we want to know where this is above or on the x-axis. So looking at the graph that we have, the part that's above or on the x-axis appears to be this part right here. So once again, we have to find the x-intercepts. So if I do second trace 0, we end up with -2. A lot of times you get crazy decimals for these, but both of these are actually going to be nice because I have something else in mind to show you here. And this one comes out to 2. So where we are above or on the x-axis is between -2 and 2. That's your answer in interval notation. You can give your answer as an inequality instead if you prefer. And you do have to be familiar with both of those representations next year, the interval notation and the inequalities. Okay, so that's the solution to that problem. I want to show you the graph on Desmos real quick for anyone who didn't believe me that that actually goes below the x-axis and stays down there. Okay, so here's that graph in Desmos. Here's the x-intercept of 2. Here's the other x-intercept of 2. And the graph goes down and it comes back up. And that can be a little hard to see, but on Desmos, I can so easily zoom in. And you can see that we're underneath, and then we continue to stay underneath. And you can even put your cursor on there and slide out to the left, and you can see that the y value is staying underneath. Now, at that point, it did appear to become 0. You don't actually hit the x-axis again. What's happening is it's getting so close to 0 that even Desmos is rounding it to 0. But you are technically staying underneath that horizontal asymptote all the way out to the left. Okay. And just to take you back to the example at hand, as I mentioned, the numbers actually came out suspiciously nice because what I want to show you is for this example, you can use the same technique I just showed you. So if we look at solving, this is your other calc preview for next year. Okay, so if we look at solving this inequality, it's quite complicated, but we can factor. This term and this term both have an e to the x. So I'm going to take out the e to the x. And then I have a difference of 2 squares. And we can't set each factor equal to 0 because it's an inequality. So just like we can't take the square root of both sides because it's an inequality, even if we wanted to. What we need to do instead is we need to make that number line. So when we make that number line, we put the points where this expression would be 0. So when x is -2, the expression will be 0 from this factor. When x is 2, the expression will be 0 from this factor. And when is this factor equal to 0? When does e to the x equal to 0? Never. E to the x equals 0 has no solution because your regular e to the x graph has a horizontal asymptote that it never hits. So this yields no additional solutions in terms of special points for our number line. So think back to the previous example. What did we do to figure out where we should put a plus or a minus for these 3 intervals, these 3 regions? There aren't always 3 regions. There just happen to be 3 regions in this example. what we do is we test an x value. So we test something to the right of 2, like 3 or 5 or 7, and we plug in to this function, and I don't need the actual numerical value. I just need to know positive or negative. So if you plug in 3 here, e to the third is positive. If you plug in 3 here, it's negative. If you plug in 3 here, it's positive. And a positive times a positive, it's a negative. See how this is below the x-axis to the right of 2? That's how it goes together. Between -2 and 2, you can test 0, you can test 1, you can test -1, whatever makes you happy. Anything between -2 and 2. And if we plug in 0, we don't care about the numerical value, we just need to know positive or negative. E to the 0 is 1, that's positive. Plugging in 0 here gives us 2, which is positive. Plugging in 0 here gives us a positive. Positive times a positive times a positive is a positive. So between -2 and 2, that test point represented all the x's between -2 and 2. This inequality would be greater than 0, which is why the function is above the x-axis in that region. And finally, to the left of -2, let's test -3. So I have e to the x times 2 minus x, and times 2 plus x, and we're going to plug in -3. So for e to the -3rd, that's 1 over e to the 3rd. I don't need to know the actual value. I just need to realize that that's positive. As weird as that is, as unusual as that is, it's positive. And 2 minus -3 would be positive, and 2 plus -3 would be negative, and a positive times a positive times a positive is a negative. So for this particular problem, we actually did not need to graph to solve. But the graphing calculator is one of the things I wanted to practice today. So sometimes next year, even when it's a strange looking function, you might be able to do this technique to solve algebraically for above or below the x-axis. If the function is less friendly or you get some crazy decimals involved, then we could use a calculator to find the same solutions. All right, thank you for watching today's lesson. And I'll see you at the next class for our final lesson of the year. Take care, guys. Bye-bye.